Okay, so we have this. All right, so we'll look at our data then from a couple slides back, and we'll do an ANOVA analysis here. Okay, so I'll just copy this over. And we'll fill out an ANOVA table. Okay, so we'll create ANOVA table. So we have our source, which will be between, within, and yeah, we'll just leave it at that. Okay, and then we'll have total. All right, so our degrees of freedom. How many degrees of freedom will we have between the groups? It's number of groups minus 1, so we have 2 degrees of freedom. Okay. How many degrees of freedom will we have total? Well, we have 12 data points, so we would have a total of 11 degrees of freedom. So our degrees of freedom within will be 9. Great. Okay. Okay. We'll go for our sum of squares. Okay. So the sum of squares between is going to be the group mean minus the grand mean. So previously we calculated the grand mean to be equal to 13. So our sum of squares within is going to be 11 minus 13 squared. What did I say? Oh, I meant between. So this number up here is going to be 11 minus 13 squared, and I have 3 data points, so I'm going to multiply that by 3. Plus, the group mean is 15 minus 13 squared, and I multiply it by the fact that I have 5 data points. And then I'm going to do 12 minus 13 squared times 4. Okay. So this becomes 3 times 2 squared, 4, plus 5 times 15 minus 13 is 2. 2 squared is 4, plus 12 minus 13 is 1. 1 squared is 1, so 4 times 1. So I have 12 plus 20 plus 4. And my sum of squares for between is going to be 36. Okay. They give us our standard deviations. Okay, so we're going to do n minus 1. So 3 minus 1 times s squared, 4.359 squared. I should have written this in a bigger section of my paper. And then I get 5 minus 1 times 4.95 squared, and then 4 minus 1 times 4.967 squared. Okay, so let's do this. 4.359 squared times 2 plus 4 times 4.95 squared plus 3 times 4.967 squared. Okay, so I get 210. Okay, so actually, so I'm going to just kind of write my table over here again. So I got source, df, sum of squares. Okay, so between, sorry, if your table can just be expanded to the right, do that. So I got 2, 9, I have 36 210. So I have a total 11. I'm going to have a total of 246 for sum of squares. My mean squares is going to be 36 divided by 2. So my mean squares here is 18. And over here, my mean squares is going to be 210 divided by 9. So 210 divided by 9 is 23.33. Okay, and if I did 246 divided by 11, that would be my total variance, 22.36. This is our variance. Okay, and our F ratio is going to be 18 over 23.33. And I got 0.7714.
Where did you get 18 from?
The mean squares. Okay, so this is my ANOVA table right here. Okay. And then what we would do is we would look up this value in an F table, and the F table has a numerator degrees of freedom and a denominator degrees of freedom. Okay? So our numerator degrees of freedom is 2, and our denominator degrees of freedom is 9. And I think that makes sense, right? Because when we create our F ratio, we have 18 on the top, and in that row, the degrees of freedom is 2, and 23.33 on the bottom, and in that row, the degrees of freedom is 9. So we have a numerator df, which is going to be 2, and our denominator, I don't know how to spell denominator. I don't know how to spell a lot of things. So our numerator degrees of freedom is 2, and our denominator degrees of freedom is 9. Okay, and so we would look this up in our F table. Okay, now if you had in our textbook, well, okay, the 4th edition of the textbook has the F table, and the 5th edition of the textbook, they were like, we are going to save ourselves a penny and not print the F table in there. But if you have the 4th edition, it's in the very back of the textbook. It's table something, table 10. Here it is. Okay, and you would go. There's one page for every single numerator degrees of freedom. So it starts off with numerator degrees of freedom 1, and then there's 10 pages of table 10, each for a different numerator degrees of freedom. Okay, so all we would do is we would go to numerator df2, denominator df9, and then we would look up our test statistic, which was 0.7714. Okay, and what do we see? We see our test statistic 0.77 falls over here, right? It's less than 1.93. So therefore our tail probability, which would be our p-value, is greater than 20%. Okay. So what we would find is our tail prob is greater than 20%, which means our p-value is greater than 20%. Is that okay? This F table is quite unique. Well, it's not that unique, but most textbooks don't give you 10 pages of the F table. They'll give you 2 pages of the F table. And if we looked up an F table online, it'll look very different. It would look something like this. That is really small. Okay, so what you would have is you would have maybe 1 table or 2 tables. This is the alpha 0.01 table, and probably they would have you would get two tables of the F table. One would be the 1% F table, and then the other one would be the 5% F table. Okay? And basically, all this does is give you one critical value. And it says if your F ratio is bigger than this, it's significant at the 1% level. And if it's smaller than this, it's not significant at the 1% level. And you would look up the numerator degrees of freedom up here and the denominator degrees of freedom down here. So we would go to 2, 9, and we would get 8.02, and we'd say, oh, my value of 0.77 is less than this, therefore my value is not significant at the 1% level. Okay? We can see that if I went to the 1% column here, that these values line up. So effectively, so this value 8.02 is right there, and 7.56 is right here. So effectively, it's just taking this 1% column for numerator degrees of freedom equal to 2. Okay? And then for numerator degrees of freedom equal to 3, it's just taking the 1% column. Okay, and that's so it gets 6.55, 6.99, so on and so forth. All right. Is that okay? So all it's doing is it's just so I would say this is the more common format for an F table, where they only give you 2 pages of the F table, and you look up the numerator degrees of freedom in the column, denominator degrees of freedom in the row, and then you just say, is my critical value bigger or smaller? I mean, is my test statistic bigger or smaller than the critical value provided in the table? And if it's bigger, it's significant at the 1% level, and if it's smaller, it's not, or whatever level the table is associated with, usually 1% and 5%. Okay. Okay, so what we get is our p-value is greater than 20%. Okay, or if we use the other table, we'd say our p-value is greater than 1%, or our p-value is greater than 5%, whatever table we use. Okay, so let's so what we have is our p-value is greater than 20%. Okay, what was our null hypothesis? Yeah, that mu1 was equal to mu2 equal to mu3. Effectively, that all diets have the same mean weight or have the same effect. Or have the same effect effect on weight gain. Okay, and then the alternative was at least one diet different. Okay, and so we have this, and then our p-value is greater than 20%. So what does this mean? This means that if all the diets have the same effect on weight gain, what is the probability that a random sample would produce results like ours, results like our data. Okay, because in our data the group means weren't all the same. We had one group mean 11, another group mean 12, and another group mean 15. So what's the probability that a random sample would produce 3 group means that are as different as that? Well, the answer is those results, it happens these results would happen with probability of about 20%, greater than 20%, okay? Okay, and so what we would say is that, you know, we therefore cannot discount or disregard the possibility that our data resulted from chance. Okay, so we do not reject the null hypothesis, and would say we do not have evidence that any of the diets have a different effect on weight gain. Okay, are there any questions on this? All right, and so then I'll continue on here. Okay, let me show you how this analysis can be done in R. Okay. All right, so what I'm going to do is I'm going to just input this data here, okay? So I'm going to call, these will be our weights as a vector, and it will be 8, 9, or 8, 6, 16, 9, comma, what do we have? 9, 16, 21, 11, 18, 15, 10, 17, and 6. Okay, I put them on different rows just for my own readability, but R ignores blank spaces and line breaks, so it effectively is just one line with all of these entries. Okay, and then I'm going to have labels, or I guess the diets will be, I've got A, I've got 3 in group A, and then I've got 5 in group B, and 4 in group C. Okay, is this okay? All I've done is I've just put in my weights, whoops, which is just a row of 12 numbers, and then the diets is just a sequence of 12 letters. Okay. Now, if you put diets 1, 1, 1, 2, 2, 2, 2, 2, 2, and 3, 3, 3, 3, 3, if you used numbers, R is going to see that, and it's going to say, oh, these are numeric variables, and it's going to treat this as something that those in group 3 have 3 of something, and those in group 1 only have one of that thing, okay? So it's gonna say, oh, group 3 is getting 3 times as much whatever as group 1 because it sees it as a numeric variable, okay? And so if you can enter them as numbers, but then you have to say these are not numbers, these are labels, okay? So if you see 3, don't treat it as the number 3, just treat it as label 3, okay? When you give R letters, it's gonna say, okay, these are labels. So that's why I've chosen to use the letters A, B, and C. But I could have used numbers, but then you have to tell it, don't treat them as numbers, treat them as labels, and the term for that is called a factor, okay? And the command for this is you use this command called AOV for analysis of variance, okay? And basically, I'm going to just say, do analysis of variance where the weights tilde diets. And this just means explain the weights based on diets, okay? And then I'm going to just store this in an object called results. I could just call this whatever I want to call this, blah, 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 but I'm just calling it results, okay? But the command here is AOV. AOV weights tilde diets. So it says explain these numbers based on these labels. Okay? And boom, done, okay? And then so I can ask now, all right, tell me what my results look like. Okay, and then so we just say, give me the summary of the results. Okay, because I've stored the output of the AOV command as this object results, and now it says, okay, so give me a summary of that output. And when I do that, it gives me this, okay? Degrees of freedom for diets 2, residuals 9, 36, 2, 10, 18, 23.3, 0.771, and that is not what I wanted to do. Come on, computer. We can see that these values match exactly with what we got by hand, right? So our degrees of freedom, our sum of squares, mean squares values, and our F statistic, all of this matches exactly what we have in our table, and and here it gives you the p-value in the table as 0.491. Okay, when we did it, we just said p-value is greater than 20%, right? Now I could show you that. You know, what's the what did I do? The variance of our weights is indeed equal to the mean squares right here. Okay. So doing ANOVA, building up this table, is really just 2 lines. Okay, it's just a matter of getting your data into R, and then building. And it's just running these 2 lines, okay? If you had it in a spreadsheet, you would just be like 1 line to get the data in, and then you'd have 2 lines to do the analysis, okay? So that's kind of neat, yeah? Okay. What's that?
Is this not 5?
No, I was, you know, I wasn't gonna make you guys do this, but I mean, if you want a lab, no. Huh? What's that?
Just like for problems on my homework.
So the thing about the problems on the homework are not designed to be analyzed using R, because R is meant to handle like raw data, and I don't know if there's a analysis of variance command for dealing with summary values. Okay, and then so in your homework, it doesn't give you the raw data values. It won't, in the homework, you won't have the actual 12 values of the individual lambs, okay? You're gonna just get these summary numbers. So the homework's just gonna give you kind of these values, the n, the mean, and the standard deviation. And based on that, you can generate the ANOVA table, okay? So You can try, but you probably won't be as successful. Okay. Okay. So anyway, I think this is a common thing to appear. Rarely in research articles don't generally publish the ANOVA tables anymore. They used to back in the day. Okay. Now they just print the p-values. But I think if you take additional statistics classes, I would say a good class, depending on your future path, a good class to take next would either be regression, which is what we're going to cover next week, or a good next class would be ANOVA/design of experiments. So usually if you take a class called design of experiments, there will be a heavy ANOVA focus on it. And it's a very practical class in terms of understanding how to set up an experiment and understanding how to analyze the data from it. And so you'll really understand, learn where this table is coming from. Okay. Okay, so that is one way ANOVA. I want to kind of just mention some of the other forms of ANOVA that exist. Okay, so for one-way ANOVA, you have basically one categorical source of variation. Okay, in addition to the always present residual source of variation. Okay, so with one-way ANOVA, you have one categorical source of variation. Okay, in addition to the always present residual variation. Okay, and then the model, the quote-unquote model that one-way ANOVA works is it says that each individual data point, y sub I or x sub I, whatever you call it, this consists of a grand mean plus a group effect plus, so it says basically each value in your data is equal to the grand mean plus a group effect plus what's called residual error, basically individual difference. Okay, so basically it says, why is that man 6 feet tall? Okay, well, it would be that man is 6 feet tall because the average height of all humans is, so 6 feet tall would be 72 inches. So it would be the average height of all humans is something like 67 inches. The fact that he is a man puts his group average 3 inches higher. And because he is on the tall side, he himself is 2 inches taller than the group average. That's how we get the value 72 inches. That's basically what it's saying. All right, I don't know if that makes sense. Okay, so that's one way ANOVA. All right. Then we have, I guess this would be called randomized block ANOVA. Or we'll say the randomized block design ANOVA. So the ANOVA for this. So basically we have two sources, two categorical sources of variation. And so here our model for each data point would be the grand mean plus the group effect plus the block effect plus the residual error. Okay, so the two categorical sources of variation, I should split this up into one is of interest, and then the other one must be, quote, accounted for. Whatever. Okay. Okay, so this basically, you know, the same things, and this is just would be the block effect. So same labels as before. And it basically says, you know, and any of these, of course, the group effects could be positive or negative. Okay? And so here we have a block effect thrown in there. All right, so what is a block design? Okay? And what does it mean to have two categorical sources of variation where one is of interest and one must be accounted for? Okay. So sometimes in the course of designing an experiment, you might be interested in the effect of a treatment on your response. Okay, so you know, maybe you are interested if the diets cause the different lambs to gain weight. Okay, but we also know other things are at play. Okay, so there might be different reasons why lambs gain different weights. Okay, perhaps you are on a small farm, and how many lambs are born to a mother at one time? I have no idea. Are they like one kid at a time, or is it? Do we know? Or is it like dogs where they're like 6 are born at the same time? I have no idea. Okay, but so it could be like maybe. Well, okay, let's say we have pigs, because I know a bunch of pigs are born at the same time. Okay, so it could be that you have like two different pigs, okay, 2 different sows, and one historically has produced heavier weight babies that gain weight faster than the other one, okay? I have no idea, all right, I'm just making this up. And so if you did not account for that difference in your analysis would not be very good, right? Because you're missing some other factors that are at play. Or here's another example. So we could have, let's say you were interested, I don't know, something stupid here. You got some plant here, all right? And we want to know, like, how fast is this thing gonna grow, okay? And you're gonna water it. Look at this beautiful picture. And maybe you're going to give it some kind of magic fertilizer, okay? Miracle Grow. I was always curious, like, does this stuff actually help the growth of plants? Who knows, okay? So you want to know, like, does the fertilizer work? Okay. Now, because you're a good experimenter, you're going to have multiple plants, right? You're not going to just have one. You're not going to just have one on the fertilizer and one without, okay? Because that's not a good experiment, because there could just be individual differences. Okay, so you've got multiple of these, all right? But let's say, and you're all going to put them into like, you're all going to put it in a controlled environment, okay? So everything. You want to make everything as identical as possible, with the exception that some of these plants are going to get treatment and some will get plain old water, right? So you got control, plain water, and the treatment will be, they get, the fertilizer. Fertilizer plus water, okay? All right, so ideally, you could make everything as uniform as possible. But let's say there's a window in your thing, okay? And the way it goes is that, or let's say we have two treatments. So we got treatment 1 is fertilizer. Treatment 2 will be, we got fertilizer A and we have fertilizer B. So we have two brands of fertilizer, and we want to see if any of them even make a difference from just plain water. Okay. So you've got a window, and because of the arrangement of the space, you can't get everything right next to the window. Okay. And so let's say with the window, this area is going to get the most sun, and this will get medium amount of sun, and this will have the least amount of sun. Right? And so what you don't want to do, you don't want to put all the control plants here, all of fertilizer B here, and all of fertilizer A here, or something, okay? Because we know sunlight has an effect on plant growth, okay? So if you put all, so bad design would put, control here, fertilizer A here and fertilizer B here, okay? Because at the end of the experiment, let's say the results show fertilizer B, the plants getting fertilizer B grew the most, and the control plants grew the least. Okay, so if this happened at the end of the experiment, you're in this conundrum where you don't know, well, did the control plants grow the least because the plain water is ineffective and fertilizer B is super effective? Or is it because they got the least amount of sun and the fertilizer B got the most amount of sun? Okay, so in this setup, we call the sunlight, amount of sunlight, and fertilizer type are confounded. Okay, meaning that they're like confused. You cannot distinguish the effect of one from the other because all of your data is lined up in such a way that it turns, every single plant that got fertilizer B also happened to get the most amount of sun. Okay, so this would be a terrible experimental design, and the conclusion would just be, well, sunlight makes a difference, and we don't really know if fertilizer makes a difference, or vice versa. We don't know what's going on. Okay, so this would be a bad design. Okay, so you can do a purely random design, and with a purely random design, you might get a mixture of control fertilizer A and fertilizer B in this zone, and a mixture in this zone, and a mixture in this zone. Okay, but because it's random, it's also possible that you still get like a bunch of fertilizer B plants over here and hardly any fertilizer B plants over here. Okay, so a purely random design helps fix this, but it doesn't guarantee that the design is balanced, if that makes sense. Okay, so let's say, I don't know, we want to really be thorough and we wanted to have 6 plants in each zone. Okay. Okay, now with fertilizer, with a purely random design, it's still possible that maybe 4 or 5 out of the 6 end up being fertilizer B. Okay, randomness should help control for that, but it's still possible for something to get messed up. Okay, so with a random design, a purely random design, okay, all of the control plants should not end up in the same zone. Okay? But at the same time, it's, you know, but a balanced design is not guaranteed. Okay. So enter the randomized block design. With the randomized block design, you treat the different zones of sunlight as what we call blocks. So this is most, medium, and least, right? And what this will do is it's going to make sure that within this block, you're going to get 2 control, 2 fertilizer A, and 2 of fertilizer B. Okay, mixed up, shuffled. All right, and it's gonna, and also the same in this zone and this zone, and in this zone. Okay, so we're gonna make sure that all 3 zones each get 2 control, 2 fertilizer A, and 2 fertilizer B. Okay, so all 3 zones are going to get 2 of each, and they're all going to be mixed around. Okay, so you might get A, B, B, C, C, or something like this. Okay, and you might get A, B, C, C, B, or something like that, okay? So you're going to just get kind of, they're all going to be mixed up in there, but each zone is going to have a balanced amount, okay? And that way, at the end, you can extract the, account for the effect due to sunlight, and then the effect due to fertilizer A and fertilizer B, okay? And so what you're hoping for is that at the end of the experiment, if the plants under fertilizer B grew the most in this zone and in this zone and in this zone, then we have pretty strong evidence that fertilizer B is effective in helping the plants grow the most. Okay? So, you know, at the end of experiment, if fertilizer B grew the most in all 3 zones, you have strong evidence that fertilizer B works. Okay, well, I guess by how much matters, right? So, you know, looking at the variation and things like that, of course you'd have to do the ANOVA analysis to make sure that the differences are significant, okay? But that's the idea of a randomized block design, okay? So generally, for the randomized block design, you have something that you kind of have to account for, something that we already know affects the outcome, like sunlight or something like that. Okay. The other ANOVA design, okay, is the 2-way or just factorial design ANOVA. So in this case, you know, so we can do like a two-way factorial design. So two-way factorial design has two categorical variables of interest. So both variables are of interest to us, and we are also interested in the interaction between these variables. In the quote interaction, or we might call this synergy between the variables. What's that? Okay. So, for example, I'm trying to think of an example here. So, you know, what is it? What is the idea of this interaction? Interaction or synergy effect? Okay, so maybe maybe you can run an advertisement to promote I don't know, sales of something here. Okay, so maybe you can run a TV ad. Okay, and generally, if you know, sales, let's say sales without the TV ad, let's say average, I don't know, $1,000 per week or something like that, okay? And then when you run TV ads, we'll say sales with the TV ad maybe is $1,300, okay? And so therefore, we can say the quote effect of having the TV ad is something around $300, okay? Okay, and then maybe we have radio ads. Okay, and then so we have sales without radio, we'll say is like 1,000. Okay, and then sales with the radio, we will say is like 1,200. Okay, so we'll say the effect of radio is maybe something around 200. Now, what could be, so what we would expect is that if we ran the TV ads and the radio ads together, we would expect something around 500 total, right? So with TV and radio together, okay, we expect something like, you know, 1,000 plus 200, or plus 200 plus 300 plus 200. We're expecting something around 1,500. Okay? But maybe what actually happens, actual sales, maybe it's something like 1,800 or something like that. Okay? It's possible, right? And so what that means is the customers are responding much better when the TV and the radio ads are played together rather than when they play individually. Okay? It's like getting, you know, we're getting a free bonus. So there's a quote interaction effect of about plus $300. Okay? So we're getting something much bigger than we would anticipate when it's by itself. Does this kind of make sense? Okay, and so this is accounted for in the factorial design, and so our model here and if you pick up another textbook, they might all use different letters, okay? So here our model is something like mu plus tau plus beta plus gamma. Okay, so this would be grand mean. So every individual value is the result of the grand mean plus factor 1 effect. So this might be the TV plus this is factor 2 effect or treatment to whatever you want to call it, and then the gamma, this is our interaction plus residual error or individual differences. Okay, let me see. Let me just check the textbook, make sure I'm kind of covering what needs to be covered. Okay, that's okay, and so that's kind of what we have with factorial ANOVA. So this was two-way ANOVA, having two factors. You can expand this to have like 3 factors or 4 factors, and then you would have additional interaction terms because maybe there's it just gets more complicated. Okay, because maybe there's only an interaction between factor 1 and factor 2, but not an interaction between factor 2 and factor 3. Okay. Or maybe there's an interaction when all 3 are together, but not when just 2 of them are together, okay? And so all of those would get added into your model. So when you say, this individual value, it consists of the grand mean plus the effect of this factor, this factor, this factor, plus the fact that when all 3 factors are together, it does something, or, whatever. Okay, so your model just gets more and more complicated as you add more factors. If you were to take a course on design of experiments, they would cover all of this in great depth and detail. Okay, here I'm just kind of mentioning that these other models exist. What you are responsible for knowing would just be one-way ANOVA and kind of the generation of this table for one-way ANOVA. So this is, as far as ANOVA goes in this class, this is what you are responsible for learning, the calculations and all of that stuff, and the relevant hypotheses and things of that nature. Okay. Next week we have a quiz. It will cover the chi-squared goodness of fit test, the chi-squared test for independence, and one-way ANOVA. You will have to make use of the chi-squared table. You will not need the F table. Okay, so I'll have you on the quiz. You're going to have to kind of recreate this ANOVA table, and I'll ask you like what's the F ratio going to be and things like that. But you don't need to look it up in the F table. I figure if you know how to use the chi-squared table and T table, you'll also know how to use the F table. Okay, so it's not that big of a deal. Okay, we'll end a little bit early today, unless anybody has questions or anything. Probably not. Okay, well, have a great week. We'll see you guys next week.